Hey guys, this is Professor Janacek. I just want to go over a quick rundown of how the formula for the length of a curve was derived. I'm not going to go through all the details, just a little overview so you can get the basic idea. So we're going to start with a curve. Let's call it F. And on this curve, let's go ahead and identify 2 points between which we want to determine the length. So I'm just going to go from this point here to that point there, and I want to determine the length in between. To make this easier, let me go ahead and identify the x values for those points. So we've got A and B. Now what I want to do next is kind of develop a little right triangle, use some trigonometry to get us started. Actually, we're not even have to go into too much trigonometry here. But I've got this little right triangle. Let me go ahead and redraw this so it's a little easier to see. There's my right triangle. This, of course, is A. This is at B. Let's go ahead and label these. I will call this the x value and this the y value. And this is approximately, the hypotenuse there is approximately the length that I'm looking for. Granted, I recognize that my original function is a curve here, but I can approximate it with this line. I'll call that L because it's the length that we're looking for. Now, one thing we know is that L squared is equal to x squared plus y squared. All right, that's pretty simple. Let me go ahead and take a moment and write this in terms of A's and B's. So we know that x is the distance between A and B, so I can write that as B minus A, the distance between A and B. And y is the distance of the function values. So that would be the distance between f of b and f of a. All right, hopefully that's clear so far. The next thing I want to do is I'm going to factor out the b minus a parentheses squared. So if I factor that out, I end up with 1 plus f of b minus f of a squared over b minus a squared. Now, if that's a little hard to follow, all you need to do is go through and distribute that b minus a squared, and you'll see what you end up with is that little bit above. All right, I'm going to go ahead and clean this up just a little bit. And let's see, that gives us in the back, I can write this whole term as being squared. Okay, hopefully that wasn't so bad. Now what I want to do is I want to take a look at what is L. I'm going to move over here just to give myself some more space. So L would be the square root of all of this stuff, right? Another thing I'm going to do is I'm going to commute those terms because I'm going to want that b minus a in the back. All right, so now I just have L, and I commuted those so that the b minus a squared is in the back. Not a big deal. I could also go ahead and take the square root of b minus a squared. Now, I can't take the square root of this stuff here in the front. Yes, I could take the square root of 1. Yes, I could take the square root of this term that's squared. But because it's a sum of these two terms, oh, by the way, I don't need that there. Since it's the sum of these two terms, though, I cannot take the square root of that. I cannot take the square root of a sum. But this term here in the back, since it's just being multiplied to everything, I can take that one out. Okay, now it's looking like something we might have seen in Calculus 1. Let me take a moment and rewrite these things back in terms of x's. So this f of b minus f of a over b minus a, that should be familiar. It kind of looks like our derivative, or at least the distance formula. We can write it as a derivative if we make a few assumptions. Again, I'm not going through all the details here, but you'll notice that this b minus a, that's the change in x. F prime of x is f of b minus f of a over b minus a. Of course, it's going to be the limit of those. So let me just make sure you understand that there's some calculus going on in here. So this is over n subintervals. Of width delta x and the ith subinterval contains x sub I star. Again, that's really a concept that you would have seen back in Calculus 1 when determining what the derivative is, what the definition of derivative, which means I could actually kind of rewrite this now as the limit as n goes to infinity of the sum, I goes from 0 to n, of this whole mess, but now I'm looking at x sub I star, and delta x becomes dx. And of course, this is our Riemann sum. Again, the idea of the definition of the integral back from Calculus 1 gives us something like, actually this one would still stay delta x. This one now changes to dx. Dx is really an approximation, the limit of the delta x's. And there you go. Again, I recognize that these steps in here use a lot of calculus. I'm using the definitions of the derivative and the definition of integral. So make sure you remember what those are. And so here at the bottom of the page, we have a function f, and f prime is continuous on the interval from a to b. Then the length of the curve from f of a to b f of b is, there it is, what we just came up with. Turns out you can also have a function in terms of y. So here I have a second one where g is a function of y, but it ends up being the same thing. So that's the important thing. If all this stuff at the top doesn't fully make sense, just take your time with it. But the main idea is knowing the formulas. So you could actually get by just by knowing these formulas here at the bottom, and they're essentially the same. But I wanted to go through that, make sure you understand kind of where it came from. Enjoy!